Hi everyone, welcome to this new series of tutorials on geostatistics. My name is Giulia, I'm a research scientist at IBM, and in these videos I'll be covering some basic concepts from geostatistics using the GeoStats.jl project. Given that this is the first video in the series, I would like to introduce myself a bit better. I'm born and raised in Recife, this beautiful city you see here in the bottom right, which is the capital of the Pernambuco state in Brazil. There I did my bachelor's and master's degree in computational mechanics at the Federal University of Pernambuco. And then I moved to the US to do my PhD in geostatistics at Stanford in the School of Earth, Energy and Environmental Sciences. I then came back to Brazil to work as a research scientist with IBM, where I'm developing this new theory of geostatistical learning, which is a mix of classical statistical learning theory that you see applied in machine learning, for example, with geostatistical theory, which is this branch of statistics that deals with spatial data. I'm the author and lead developer of GeoStats.jl, an occasional guitar player, and an open source software enthusiast. If you'd like to learn more about myself, please check my website here. So what's our plan for today? I think the presentation of today has two main questions to be addressed. What is GeoStats.jl, the project that we'll be using in these tutorials, and why the Giulia language, which is the programming language I've chosen to implement this project. What is GeoStats.jl? GeoStats.jl is an extensible framework for high-performance geostatistics in Giulia. And when I created this project some years ago, I had some goals in mind, which can be seen as the pillars of the project until today. So I had these 4 goals that are listed here. First, I wanted to design a comprehensive framework for geostatistics in a modern programming language, so that it's more accessible for students who are not necessarily versed in low-level programming languages such as Fortran, C++. I'd like to also address the lack of a platform for scientific comparison of the various geostatistical methods in the literature. If you work with geostatistics, if you do research in this field, you know how hard it is to compare a new geostatistical algorithm with prior art. The third goal here was to exploit modern hardware aggressively, including GPUs and high-performance clusters. And fourth, the reason why I'm doing these videos, I wanted to educate people outside of geostatistics about its existence and what is it capable of. I'm very happy that GeoStats.jl nowadays is more than just a software or a project. It's actually a real community. We've been very happy to see more users asking for feedback and support. We have some active maintainers nowadays. That's me from IBM. And there are these 2 other colleagues that I met online through this awesome open source community, Martin Visser and Martin Pronk from Deltars. We have a Gitter support channel for users seeking support, help with the functionality of the project. And we have a new updated documentation here that you can also find online for this new version 0.11 of the project. I'm very happy that the project is being used by colleagues at Stanford, IBM, and other organizations worldwide. So what is this tutorial series? What's it going to be about? I'd like to illustrate very basic concepts from geostatistics with very concrete examples. So for instance, there will be this tutorial where I will be asking the question how much gold there is in a mining site that you see here in the left, given that we only have access to a few samples from this mining site. So what happens in practice, supposing that this is a mine that you are seeing from a top view? This terrain here has a few samples collected at a few places, People went there and they dig that specific block or extracted some measurements from these specific points, and now given only the samples, they want to estimate how much gold there is left to be extracted from this mining site. One possible way to do this is to actually estimate the average amount of gold you saw in the samples, and then you multiply by the area of the mine to estimate the total amount of gold. However, if you just use classical statistics to estimate this mean amount of gold in the samples, you get a value of 0.56, which is much higher than the true average had you known the full image of the mine. On the other hand, if you use geostatistical methods, you can get an estimate of the average gold here of 4.9, which is much closer to the 50 that you see here for the true average. So in this tutorial, we'll learn how to do these estimates that are called declustered statistics, and you'll be learning how to produce plots like this that gives you estimates of this amount of gold as a function of this block side here. In the second tutorial, I would like to address this other question which is also very popular nowadays, which is the question of how good is the learning model in a spatial learning context. So suppose you have some features that you collected via satellite. Here is a terrain that I'm looking from the top again for some farms in a region in Brazil. And you want to predict or create a model that predicts the crop type, which is manually labeled here in the right. So the different colors here mean different crop types. So this is corn, this is rice, or this types of crops illustrated in the color here. And the question we have is there any way that we can train a model and know beforehand what's going to be the error of applying this model in some other place? In this tutorial, we'll be learning how to assess this question, which is we'll be able to split this data set into some training and some test with the framework, and then we'll be able to run traditional learning models like a decision tree to predict this crop type here in the left. Given that we have access to the actual crop in this region here in green, we can compute the actual error of this model, which is this true error here of 24% of the samples being misclassified. If you use traditional methods from statistical theory to estimate this error, which is cross-validation, leave one out on this training set, you get an estimate of the error that's super optimistic, about 12% misclassification. It turns out that this super optimism is partially caused by spatial correlation. And as we will see, there are many better methods in geostatistical theory that allows you to estimate this error in a way that gets closer to the true error of 24. So in these two previous examples and tutorials that are coming in this series, we noticed that the spatial correlation is quite important in order to get unbiased estimates of this, variables, resources, and so on. In this tutorial here, I'm planning to address the question of how to estimate spatial correlation in general. So suppose you have some images of some variables or features that you're looking, say from satellite or from some other measurement device, and you want to address the question of how much correlated is one pixel here to the nearby pixels. You observe that this image here is very smooth. It transitions from high values represented with a bright yellow to low values represented by this dark purple color here. And you can actually see, if you look very carefully, that each of these features has a blob or an ellipsoidal shape that you can actually draw here schematically at the bottom. This ellipsoidal shape has a major axis capital R, and a minor axis, lowercase r. Geostatistical methods allow you to estimate this correlation length in the horizontal direction r. In this case, it's 30 pixels, which I'm assuming there's no units here. I'm just counting the pixels as units. And if I look at the vertical direction, there are 10 pixels of correlation. We will also learn how to produce this variogram plane plot, which allows you to learn this correlation length for any angle of your choice. We will also have tutorials on how to create synthetic 3D geological models. This is quite important when we want to test, for example, hypotheses about different geology or different conceptual geological models. So I'll be explaining how you can use GeoStats.jl to build very large, let's say, voxel models like these ones here, where you actually have, I think, 1000 by 1000 by 500 voxels in this model, and you can generate hundreds of these very efficiently. This is for smooth stratigraphic processes, where you see that these layers are very smooth, very horizontal, but you can also create very complex 3D models like these ones here at the bottom, where you use multiple point geostatistical methods to create the patterns of the surface and to stack them. So I hope you are motivated with this tutorial ideas. If you have suggestions of more tutorials, please leave a comment. I'll be happy to take suggestions and try to prepare some tutorials on that. I will now move to the second question of this tutorial here, which is why Giulia and why not Python or R? I get this question a lot, and that's understandable given that Python and R are very popular languages. And I think to address this question, I need to give some background here, which is this story here that I'm calling the workflow of the 90s, when you want to go from research to production code. So the workflow usually starts like this. You start with some Python or R code to prototype some solution for a toy example. So you get a small image, you get some small data set, and you start playing around with your ideas. You then increase the problem size and start to struggle with low performance. You rewrite portions of the code in vectorized form. That is, if you're using Python, you start calling NumPy as opposed to implementing for loops in Python directly. You add some new feature and you realize that it cannot be vectorized like the others you had before. At the end, you realize that you have to rewrite the whole software in some low-level language such as C, C++, or Fortran in order to deploy in production. This is known in the Giulia language community as the two-language problem. You have high-level languages such as Python, R, and MATLAB that are great to quickly prototype solutions, and they work really well if the heavy computation is deferred to some low-level language such as C or Fortran. However, they fail miserably if the algorithm is not vectorizable. And as you see in these tutorials, I hope to get to this point, the geostatistical algorithms are hardly vectorizable in the sense that you always have to loop into the pixels of the image, searching for neighbors and doing very local operations that are not easy to vectorize. On the other hand, low-level programming languages such as C, C++, and Fortran, they're great for high-performance software. On the other hand, they're terrible for generics. I'm using this term here, which is famous in the C++ community. I used to program in C++ in the past, which is C++ that template metaprogramming nightmare. It's very hard to write generic code in C++. It requires a lot of lines of code. So some solutions in the Python community were proposed, like the Cython, Numba, and similar projects. They are solutions that address partially the issue of low performance. Why they do not address the issue fully? There are at least two reasons why they do not address this performance issue. First, they only translate a subset of the language. So if you're doing research and if you need to do something exceptional or something different than the standard application of or standard usage of existing libraries, you always find yourself getting into a corner where the subset doesn't work. There are still two languages involved anyway, so the compiler cannot optimize the code when it reaches this switch point between Python and C, for example, or R and C. So the Giulia language came out with this primary focus on scientific computing. It has some state-of-the-art packages in various fields despite its recent state. And of course, it's still maturing. I wouldn't say it's ready for production yet, but it's perfectly ready for research. In order to go further addressing this question, I would like to share some code here now. I think it's better to demonstrate it than actually try to explain why it's important to choose a language like Giulia for this project. So here is some example code. I will try to benchmark a simple function here to compare the different implementations in different languages. This example was adapted from the Giulia Computing Giulia Box tutorials. It assumes that you have Python and R installed in the system. What we'll do here is we will try to get this vector of 10 billion entries, for example, a random vector here with entries in between 0 and 1. And we'll be benchmarking various implementations of the sum function. So if you run the sum function on this vector, you get this floating point number. We know the result beforehand because these random vectors are uniformly distributed in 0 and 1. So on average, you get half of the values when you sum. So it's 0.5 here, or 5 10 to the 6. And here I'm gonna be showing various implementations of the sum function with Python, R, C, and Giulia. So the first implementation is the Python implementation. So in Giulia there is this package called pycall that allows you to call Python code from Giulia. So here is some Python code that I write in a string, and I prefix this string with this py prefix. This interprets this string as Python code, and so I can create this function here, pysum, that calls this pysum function implemented in Python. It returns here this Python object. Similarly, I can get the built-in sum function from Python with this Python built-in call and save in a Giulia function called Python built-in sum. I can check that the Python implementations match with the Giulia implementation by checking that the result is approximately equal to the built-in sum function of Giulia. It takes some time because the Python implementation is a bit slower, is actually much slower than the Giulia one, as you will see, but the result matches. So this is the Python implementation, as you see. You write an accumulator, you loop over the vector, and you accumulate the value. I'll do something now which is also called the NumPy sum implementation here. I'll import the NumPy module, which is installed in my Python installation, and I'll get the sum function from NumPy. You'll notice that this is much faster to evaluate than the Python sum function. I can execute it again. I think it was having some delay here. It's much faster. Now I'll go for the R implementation. For the R implementation, I'll use this rcall package, which is another Giulia package that allows you to run R code from Giulia. So I load the package, and I similarly, as I've done with Python, I write this R code here in a string, defining this rsum function, and I prefix this string with this R prefix. This will interpret the code as being some R code, which I then save in this Giulia function called rsum. Similarly, I get the built-in sum function from R, and I again test the implementations against the Giulia built-in sum function. Here is the Giulia implementation of the sum, something like a normal user would write. You would write the accumulator, you loop over the vector and accumulate the values, very similar to the Python implementation. You can also get the Giulia built-in sum and save in another variable here, Giulia built-in sum. And finally, I would also like to add this third implementation, which is the same as the naive implementation here, but it adds this prefix macro here for SIND instructions, which is single instruction multiple data, which is an instruction that allows the processor to do some optimizations in this loop. I can test these implementations again against the default Giulia implementation and check that they are correct. Finally, the C implementation, I write some C code in a string. I load this libdl library, which is a standard library in Giulia that allows you to play with compiled objects, libraries. So I create here a temporary file to store my C library, the compiled library, and I call GCC here to compile this C code that I wrote in that string into this library, the C library. So it outputs this compiled code into the C library, adding the appropriate extension for the operating system. So I can compile this function, and similarly I can create another library where I compile with GCC, but I activate this fast math flag for GCC so that the code generated is a bit faster. Now I define the Giulia equivalent of this C function, which is basically calling this C function, csum, inside this compiled library, the C library. So I just map the C function to a Giulia function, and I do the same for the fastmath compiled function. I test that these implementations match the built-in function, and finally we're ready for the benchmark. For benchmarking, I will use the benchmark tools package. I'll put all the implementations, these 2 C implementations, the 2 R implementations, the 2 Python implementations plus the NumPy implementation, which is Fortran basically, and the 3 Giulia implementations. I then create a vector with pretty names for this implementation so that we can more easily understand the results. And here is the benchmark. I map these implementations or functions to a variable info, and then I benchmark this function call on that 10 billion entry vector X that I defined in the top of the script. So this benchmark macro will call this function some thousands of times, and will save the times required in each run. I can then take these times, the minimum of time in these runs, and divide by 10 to the 6 to get the result in milliseconds. I'll execute this loop. It will take some time because it's calling these functions thousands of times for each implementation. And while it's running, I would like to explain here how we're going to plot these results. To plot, I'll be using this Unicode plots package, which is very nice. It allows you to do plots in Unicode directly in the terminal without having to depend on some more expensive graphics and so on. I'll get the times from the benchmark and I'll sort them in increasing order, and I'll then sort the corresponding names, right, that I saved in this label vector here. After that, I will do this bar plot where I'll be plotting each implementation with the time in milliseconds. So select this and I'll run. So as soon as this loop here finishes, it will right away load the package and plot these bar plots. As you can see, it takes some time, but it should probably be ending very soon. As you see, most of this time is actually in the Python implementations. The bar plot will show the difference in times here. Besides plotting the times, I will also be plotting the speed up, which is basically taking this lowest time and dividing by all the times here. So here's the result for the times themselves. These are the times in milliseconds to run the sum function. As you can see here, there's already a pretty big difference between Python, R, and Giulia and C. NumPy is Fortran, so that's why it's here in the middle. But you see that the fastest implementation here is the implementation I did by hand, with the only difference that I actually wrote that prefix Cindy macro to instruct the processor about the Cindy instruction. The second fastest implementation is the Giulia built-in function, so the sum function that comes with Giulia. You see that as an end user, I could write a sum function that's even faster than the built-in Giulia function, and that's very nice. It allows you to optimize your code. It doesn't limit you or put some bottleneck on the amount of speed you can get. The third fastest implementation is the NumPy one, which is a Fortran implementation. Then you get the C with the fast math flag activated, and then C without the flag activated. Then you get Giulia, the naive implementation that a normal user would write, not caring about performance, for example. And then you have a big jump here to R, the R built-in sum function, which I guess is also implemented in two languages. I'm not sure, I would have to double check. And then the pure R version or pure R implementation of the sum, which is already a massive difference to a pure implementation in Giulia. And finally, there's these two guys here that are the Python built-in function, the sum that comes with Python, and the implementation an end user would write. So if I get Python and I write the sum myself, I get this amount of milliseconds here compared to the Giulia version here. I compare in terms of speed up, which is what I'm saying here. So the Python one is the slowest, so I give it a 1 speed up, which is no speed up. If you choose R, you get, say, 4x speed up. If you call the R built-in sum, you get 26x speed up. If you call Giulia naive, you get 140 speed up, and you can keep growing until you get to a 400x speed up in Giulia. So that's what was the rationale for choosing Giulia in this project. I hope that it's clear. I hope that I have addressed these two questions that I've raised in the beginning of the presentation. And in the next videos, we'll be covering some basic instructions for installing Giulia, this IDE of development, and the GeoStats project itself. I hope you enjoyed, and see you in the next video.